To understand the enthalpy of formation, let's have a look at this example. The carbon in the graphite form is changed into the carbon in diamond form. I can get the delta H or the enthalpy of this reaction because this is a very difficult reaction to happen under normal conditions. It requires very difficult conditions to happen. So I cannot observe and find the change in the temperature that happens and find the delta H of this reaction. But I can find it by the standard enthalpy of formation. What is the standard enthalpy of formation, or delta HF? This is the change in enthalpy, that happens when I'm forming during the formation of 1 mole of the compound or substance, or formation of 1 mole of compound or substance from its elements. So I'm making this compound 1 mole, and I'm making it from what? From its elements, the elements that it is composed of. So a degree symbol on the thermodynamic function, for example, if I said delta H like that, means that I have standard state. I am working under standard state and standard conditions. This is special conditions which will give me certain and fixed results so that everyone who is making this experiment will get the same result. So if I told you that I measured the delta H of the reaction and I get the value of 100 joules, you have to make the same conditions so that you get the same results. These conditions that we will agree about is called the standard conditions. And they have a certain values for the temperature and the pressure which I'm working in. Let's have a look again at what are the standard states. If I'm talking about a certain compound, the standard state of gaseous substance for any gas is the pressure, which is 1 atmospheric pressure. So the pressure will be 1 atmospheric pressure. If it is liquid or solid at room temperature, it should be a pure liquid or a pure solid. If it is a solution, one substance dissolved in a solvent, then the concentration should be 1 molar. What about if it is an element? What if it is an element? Then at 1 atmospheric pressure and 25 degrees centigrade, I will check what is its physical state. For example, oxygen at this atmospheric pressure and at this temperature exists in the form of gas, and the sodium, for example, exists in the form of solid, and mercury liquid, and so on, which will help us. Have a look at another example which will help us to understand the enthalpy of formation more. If I'm reacting half mole only of nitrogen plus oxygen, and both of them are in gaseous states, to form 1 mole of nitrogen dioxide gas. And we are saying that the delta H of formation under standard conditions equal to 34 kilojoules for every mole of the gas formed. I will note that the reaction is written so that both elements are in standard states. At the 25 degrees centigrade and 1 atmospheric pressure, the nitrogen and oxygen are in the gaseous state. This is their standard state, and that 1 mole is produced. So why you didn't write N2 plus O2, 1 mole and 1 mole? Because if you reacted 1 mole of this one and 1 mole of this one, you will not get 1 mole of NO2. You will be having more amount of O2, because this to be balanced, you will get 2 nitrogen. So instead of making 2 moles, I need this one to be 1 mole. So if you are talking about the enthalpy of formation, it has to be 1 mole. So by the balance, nitrogen here is 1 atom only, and oxygen is 2 atoms, so it is balanced. I will, of course, not write the 1. Okay, so 1 mole of product is formed. Enthalpies of formation are always given per mole of the product with the product in its standard state. The formation, for example, of methanol, if I want to write the standard enthalpy of formation of methanol, I will write the formation of 1 methanol mole, and it will be in the standard state, which is liquid at the standard state. The delta HF of formation of this one will be equal to minus 239 kilojoules, so released for every mole formed of the methanol. And what is the methanol is formed from? The carbon here in the standard state at the room temperature will be in the solid state, while the hydrogen in the standard state will be the hydrogen gas. So if I write H, I cannot write H, so I will write H2, and then it will be balanced. So this is 3, and this is 1, so 2. So it has to be 2 here. And the last one is the oxygen. So the oxygen has to be also half, it has to be O2 because it is gaseous state. And here we forgot to write this is gaseous state at room temperature. But because this is one atom, so I have to put half so that it produces 1 mole as agreed for the methanol. So the standard states here is solid, here is gas, and here is gas, and here is liquid. I can show some of the delta H formation of some common substances and see its values. Let's have a look at this table. Let's try to have a look here at how can I find the delta H of one reaction. So the reaction of methane with oxygen to form carbon dioxide and water, which is basically the combustion of methane. From the delta H of formation of some of the reactants and products, I know that in order to make CH4 from its elements, so CH4 is made from what? From carbon and from hydrogen. So if you added carbon and hydrogen and you formed CH4, that's why the arrow is coming from the carbon and hydrogen to the CH4, then you need negative 75 kilojoules. In this reaction, you are making C and CH4 from carbon and hydrogen. So this is negative 75 kilojoule per mole. And if you want to form carbon dioxide from carbon and oxygen, you are going to need minus 394 kilojoules. So minus 394 kilojoules. And if you want to form water, you will need minus 286. But take care, this is the formation of 1 mole of water only, but here there is 2 moles. So we have to say that this is minus 286 multiplied by 2. And we know that this is very similar to the Hess cycle. So I can say this is very similar to A and B. And then there is C, which is the constituents here. Okay, so the Hess law tells me that if you want to find the change from A to B, you can also move from A to C and then to B, from A to C and then to B. So if you want to find delta H of the reaction, which is A to B, you can just add A to C, which is this direction, A to C, which is this direction. We'll say that it's called delta H1, and then you can add it to delta H2. So if you want to move from here to here, you can move from here to here, and then from here to here, which is called delta H2. Mister, but do you have these two values, delta H1 and delta H2? Yes, I have it. This is the delta H1, and adding these two together give me delta H2. But note that delta H1 should be in this direction. We are forming methane, so I'm forming CH4, and forming CH4 here is in this direction, but I want it in the red direction, so I have to reverse this value. So I would say that the delta HR is actually equal to delta H1, which is the reverse of this value. So delta H1 plus delta H2. So it is the reverse of the value of that CH4 formation. So it is plus 75 kilojoules. And then I will add it to delta H2. We have agreed that delta H2 is actually the addition of these two together, but this is multiplied by 2. So it is minus 394. And when you add it, you will add it to 286 multiplied by 2. 286 multiplied by 2. So 2 multiplied by negative 286. And then you will add all that together and to the 75. Let's see what is the answer on our calculator. You have to be very careful here with the calculator, because if you don't make the brackets correctly, then you will not get the correct answer. Let's see what does the calculator going to tell us. So I will multiply the 286 with the 286 with the negative sign, 286 with the negative sign multiplied by 2, so it is negative 572. So this is going to be negative 572, and this is added to negative 394, so that's plus 394, which is a negative also. So we will get negative 966. So that's equal to negative 966, which is added to the 75. So 75 plus negative 966, you will get the value of the reaction, which is negative 891 kilojoules for every mole of the methane, which is combusted. So now I was able to find the delta H of the reaction, or delta H of the combustion here, from the delta H of formation. Just to simplify, what did we see here? We can say that it looked in a way or another to that. So it looked in a way another to that, that this is the delta H of the reaction. This is the delta H of the reaction that I wanted to find. I will say that it was looking like that. And this is the delta H of formation, but we know that I need to move like that and then like that. So from A to C is equal to, or let's say it's B, is equal to A to B. A to B is equal to A to C plus C to B. But in the reaction that I already have, this is the one that was wanted, and this one I have it. I have it because I have the value of the formation of A. Remember that you want to move like that, while the value you are given is actually the formation of A. So it's in the opposite direction. So you have to reverse it. And then add it to this one. This is not reversed because the formation of B is already on the correct direction. What did you mean? What does you mean by correct direction? If you want delta HR, just add this one like this direction and this to this one, because you are moving like here. We said like in the Hess cycle, moving from A to B is like moving from A to C, then C to B. It doesn't matter which is pathway you are taking. It depends only on the initial reactants and the final products. And one more thing, that we had to multiply this one by 2 because the value that I have in the formation of B was for 1 mole, but the water was 2 moles. That's why I had to multiply it by 2, and then I added the delta H1 and the delta H2 together. One more thing is that if you want to find this in an easier way, you could have just said that in order to find the delta H of the reactants, all that you have to do, so to make things simpler, is that you have calculated the delta H of the products. So this part, which is the minus 394 and minus 286, is the delta H of the formation of the products. So this is the delta H of formation of the products. And then you added it so to the delta H of the formation of the reactants. So you added to the delta H of formation of reactants, but because the delta H of formation of reactants, we had to reverse the direction, so it actually become negative. So this means that you didn't add to it, you subtracted. So again, let's say it in a different way. Let's say that actually what you did is that you said that delta HR is equal to the delta H of the formation of the products. So the products, which was here, actually let's write it with the same color as delta H2, so it was here. The products formation, the H of products, formation of the products, and then it was added to the delta H of formation of the reactants, delta H formation of the reactants. But because this one was reversed, actually it was not added, it was added to the negative. So if you want to correct this one, we can say that it is delta H of product minus delta H of reactants formation. So without making the Hess cycle, you can try to find the delta H of any reaction, delta H of reaction, by just doing this equation that we did right now. So just by doing the equation is that the delta H of the any reaction is equal to the delta H of the formation of the products minus the delta H of the formation of the reactants. Let's try to do it the same way. So what are the values here? We'll get the values from here. What is the delta H of the formation of the products actually? It is the products, which is minus 394, and then added to 286 doubled, which was minus 572, so plus minus 572. And this all was added to the opposite of this one, because this value we have to reverse it. So it was not negative 75, it's actually added to plus minus 75, which means that it was subtracted from the reactance. So it became, instead of saying plus minus, we can say that we actually subtracted it from 75. And then, of course, the value will be the same, which is minus 891 kilojoules per mole. You can do this to find the delta HR of any reaction without having to do the Hess cycle every time for the reaction.